latest in our inaugural lecture series. My name is Stuart Humphreys. On behalf of the university, I'm delighted to welcome you to this lecture by Professor Minnie Saaj. These inaugural lecture series are a way to celebrate and understand on a very intuitive level what our our new professors have been doing and what they're going to do at Lincoln. They're about celebrating the research and the research leadership of our new professors. So I'm not going to say much more. I'm going to hand off in a moment to Professor Libby John, the Pro-Vice Chancellor for the College of Science, to introduce Minnie, but I do have a few housekeeping items just to flag up. So if you could note that we will be recording this, and so it will be made available shortly after the lecture. We won't be switching on cameras and microphones for attendees, so you don't need to worry about privacy. There will be questions at the end, and if you could post those into the chat, and then we'll put those questions to Minnie, and we'll put as many across as we can in the time available. The other thing really is just to remind you that we have a series of these inaugural lectures, so please do keep in touch with us and join our mailing list if you would like, so that you can be aware of the next ones. So without further ado, I will hand over to Professor Libby John, who is going to introduce Minnie.
Well, hello everyone. It's wonderful to see so many of you have joined us tonight for this inaugural lecture. I'm really pleased to introduce Professor Minnie Saaj. She's our Global Chair in Robotic Engineering. Minnie joined the University of Lincoln in September 2019. She's originally from India, where she did all her studies. We're incredibly impressed by her passion for space research, and we're highly supportive of her desire to grow the space business in Lincolnshire, which I'm sure she will achieve. Minnie is absolutely a role model for aspiring space engineers, particularly female engineers. Minnie is an internationally renowned academic, a space engineer in a male-dominated profession, and a proud mum of 2 daughters, aged 20 and 15. I expect they're listening in too. I welcome Minnie to give her inaugural lecture, which I'm sure you will all thoroughly enjoy. Over to Minnie.
Thank you, Libby. I hope all of you can see me. Thanks, Stuart, as well, for organizing this inaugural lecture. So once again, good evening, ladies and gentlemen. Welcome to our inaugural lecture. Are you ready for liftoff? Well, have you wondered about space? I too had a passion for space since my childhood. Believe me, it's in my DNA. I'm the 2nd generation of space professional in my family. Thanks to my dad, who served the Indian Space Research Organization for 34 years. My dad used to bring the Countdown magazine. In fact, this is a scientific magazine which I used to turn over with curiosity, but I never understood a word. It didn't matter because I was not after the details. I was only interested in the colorful pictures of satellites and rockets. Secretly, my brother and we made several stickers using the cutouts. So that was our hobby. Now, it was my dream as a child to work for the Indian Space Research Organization. And we were able to, or it was indeed a privilege to do our studies at Vikram Sarabhai Space Center, which is ISRO's own school. So during my time at VSSC Central School, my passion for space grew. And when I started studying for my engineering degree program, I had the opportunity to work for the Indian Space Research Organization. In fact, my first project or space project was a BREDAS. Thereafter, I also worked with ISRO on autopilot design for launches. So when I worked with ISRO on these two projects, my interest or determination to become a space engineer started growing. Without losing much time, I went for doing my PhD at IIT Bombay with the hope that I can return back and become a scientist at ISRO. Interestingly, my destiny was elsewhere. And even before defending my PhD thesis, I landed in Hamburg to do my first postdoctoral research. So during my 5 years of postdoctoral research, I learned quite a lot about satellites, launch vehicles, landers, planetary and lunar landers, robots, which included robotic or industrial manipulators, unmanned ground vehicles, and of course, planetary rovers. So that was an exciting journey for me. Every day I was learning something new. And when I took up the lectureship, the full-time lectureship at Surrey Space Center back in 2007, I started focusing more on space robotics because I can't be everywhere. So my focus was then to grow space robotics research at University of Surrey. And of course, now I'm with University of Lincoln with a new mission to grow space research and robotics at Lincoln. And of course, we want to grow the space business locally in the Lincolnshire County. Moving on, for today's presentation, I will try to keep it focused on space robotics, but I will also show you some very interesting spin-out applications of space robotics for other sectors. In fact, I'm lucky to work with colleagues from diverse sectors, industry stakeholders from diverse sectors who are supporting spin-in or technology transfer of robotics and automation to different applications. So I'll start today with some insight into the orbital robotics research that we are doing today in Lincoln, as well as some of the previous projects I have led at Surrey Space Center. I'll also briefly show you some of the interesting outcomes of the planetary robotics research, and obviously then we will move on to some other colorful activities we are currently having in Lincoln. So with that, I'm just going to introduce the first phase of my presentation, which is focused on orbital robotics research. By orbital robotics research, what we mean is this is to look at design of satellites with robotic manipulation capabilities. Or in other words, this could be conventional satellites, but they do have robotic arms. It could be a single robotic arm or multiple robotic arms. And these are meant for doing a lot of services in orbit. Today we are going to go through some of those applications of orbital robots. Well, when I say I specialize in space robotics, I don't do everything because, again, based on my background as a control engineer, I try to specialize in automation and control of space systems, and obviously my focus is on space robots. So under orbital robotics, we work on a range of applications which looks at, say, for example, how we can service a faulty satellite in orbit. Can we extend the lifetime of a satellite, a functional satellite that is approaching its mission, end of mission? Can we repair a satellite? Can we refuel a satellite? Can we construct large structures like the ISS in orbit? And one of my focus is on assembling of space telescopes, modular space telescopes. We are also interested in applying similar technologies for cleaning up of space, or in other words, active debris removal. So these are looking at, for example, how we can capture different types of debris. It could be a faulty spacecraft. It could be other types of debris floating around in the orbit. So there are numerous applications of robots in orbit, and in consultation with various industries who are specializing in robotic missions, we are trying to develop transformative technologies in robotics, which we can apply to different application scenarios. So let me start off with some of the studies that we did in the past. Considering that this is not a technical conference, I will not be going into the details of the maths or any such technical discussions, but I'll try to keep it simple so that audience from different background who are attending or who are listening to me, you can follow me well. Now let's start off with looking at on-orbit servicing of satellites. So when we talk about on-orbit servicing of satellites, here again, one of the vital component is a robot or a robotic arm. And of course, this robotic arm is mounted onto a spacecraft, which is a standard satellite. It could be large or it could be small. Unlike controlling a robotic manipulator on ground, it is very challenging to control a robotic manipulator in orbit. This is mainly because of the low gravity condition plus the complex dynamics that affects the motion of this spacecraft. So we work on various guidance, navigation, and control strategies, looking at how we can precisely maneuver a spacecraft in orbit and how we can safely capture and deorbit a target if it is a debris removal application, or undertake the repair operation needed if it is a servicing mission. So we work on a range of path planning and control solutions that can hopefully find its way to space in future missions. I'm not going into the details of the programs or the algorithms that we develop, but I just want to show that there is a very intense level of mathematical modeling that goes into understanding the dynamics and control of a space robot. And it's very important that we as space engineers, we are able to understand the complex dynamics, and thereby, we can develop clever or, intelligent control algorithms that are needed for precise and safe operation of space robots. So this is one of the areas that we specialize. Similarly, we also look at system design. Say, for example, conventional satellites are pretty large, but of course, there is also a growing interest in looking at the potential of small satellites to undertake such servicing or repair operations in orbit. You might wonder, if it's a small satellite, obviously, it can't do much, unlike a large spacecraft. True, it's very true. So here we are looking at how small a small satellite can be. And we started off looking at CubeSats. Obviously, CubeSats can't do much if it is a robotic mission, very true. But we could have multiple such smaller space robots working collaboratively to undertake certain operations. Similarly, we are looking at scenarios or mission concepts where for example, two small space robots, each having a single manipulator, they could actually dock together to become a larger spacecraft with a dual arm feature. So these are some of the other aspects of systems engineering and system design or space robot design work that we are doing. So this is another very interesting area because there is a future, I believe there's a future for smaller satellites and small space robots as well. Another very interesting application is the potential of in-space telescopes, or how we can actually assemble modular large aperture space telescopes in orbit. If you look at the very successful Hubble Space Telescope and the next generation, which is a James Webb Space Telescope due for launch later this year, if I'm right, you will see that the aperture of these space telescopes are very small compared to the concepts or the advanced concepts that we are developing now. So we are looking into the future where we want to see the potential of constructing space telescopes with aperture more than 25 meters, 25 to 100 meters. How on earth are we going to do this in space? So this is a very challenging question for us, for everyone in the space community. And I can confidently say that there is a growing interest internationally to push robotics, automation, and AI solutions for such missions. And what we do in that context is actually looking at the robotic solution. So during my time at Surrey, I was able to work with Airbus and SSTL to develop the concept of an e-walker, which is an end-over-end walker. So this is slightly unconventional design compared to the standard robots or the robotic arms that have been successfully deployed in space. So this is a robot that can walk, but this is very different to a conventional walking rover or a robot that we use for planetary missions. So here, what we do is, again, we are looking at the design, modeling, and control of the e-walker. And what we do is, at present, we are focused more on developing the guidance, navigation, and control algorithms. And in Lincoln, we are trying to develop a scaled version of the e-walker. So hopefully, in a year or two, we will be having a functional robot which we can then use for some of the Earth analog testing. We are working with SSTL, who is acting as an industrial advisor on this project. At the same time, we also interact with other stakeholders who are interested in this mission concept. In the past, I have also had the chance to work with Airbus and several other companies on application of model-based systems engineering, and of course the use cases or the mission concepts that we focused at that time was, one was on robotic servicing. So this was connected with the German DIOS mission. And then we also looked at active debris removal, where our focus was more into looking at the power management system for a space robot. We also looked at other potential uses of model-based systems engineering. So this is really moving from a paper-based approach to a model-driven approach, which will significantly improve the systems engineering capabilities of organizations. And we are very glad to say that Airbus and other companies are already investing heavily in MBSE solutions. Now, we now have a very interesting opportunity to apply this to another sector. Of course, when it comes to space, one other area I'm interested is to apply the additive manufacturing technology for orbital and lunar missions, mainly focused on in-situ resource utilization. And of course, this involves manufacturing techniques, and we are interested in exploring how robots can support such manufacturing operations in orbit or on the moon. And now we are going to kick off a new study with our partners, Perpetual Labs, Carpenter, and Autodesk, looking at developing model-driven digital engineering solutions to make manufacturing smarter. If we succeed in this program, I'm pretty confident that we can apply such solutions for in-space manufacturing, so which goes hand in hand with in-space assembly missions. So this is another exciting opportunity we are looking forward to work with our industry partners as well as the Greater Lincolnshire Manufacturing Network. We are also working very closely with the Satellite Applications Catapult and several industry stakeholders, primarily from the space sector, to develop the in-orbit servicing and manufacturing programs. So we are part of the UK Space IOSM working group, and we are working with all these industry partners, UK Space Agency and Inaugural, to develop new mission activities focused on in-orbit servicing, assembly, and manufacturing. So this is different to the planetary robotics research or planetary robotic missions you might be more familiar with. So this is a trend now, because we have realized that, there is a real need to enhance the capabilities of orbital missions through using advances in robotics, automation, and AI. If you look at ground-based application of these technologies, they are far ahead of what we are currently using in space. And there is a huge potential for spin into space, and this is one other area I'm interested in. So I hope with support of all these industry partners and funding agencies, we will be successful in having new programs focused on in-orbit servicing, assembly, and manufacturing missions. I would like to thank our Vice Chancellor, Professor Mary Stewart, and Pro Vice Chancellor, Libby John, for kindly introducing me to our local MP, Mr. Carl McCarthy. He listened to our space initiatives with great enthusiasm, and I'm pleased to report that he is now representing us at the UK Space Parliamentary Committee. We are also getting similar support from Member of Parliaments from various other counties through our industry partners. So I believe with support from government, with support from various entities, we will be able to grow the National Space Program focused on IOSM in near future. Let me also say a few words about some other initiatives that we are part of. Thanks to KTN and the UK Space Agency for pulling together this very interactive and useful sector map. This is a very useful tool for identifying partners who are working in the space industry or academia. And I'm pleased to report that University of Lincoln is now in their radar, which is great, considering that we are young in terms of developing the space research in Lincolnshire. So this is a great opportunity for us to also collaborate with other leading parties in this game. I'm also coordinating another interesting initiative, which is to develop a space robotics technology hub through the Space Academic Network. So this is really looking at the potential of growing UK's capabilities in planetary robotics as well as in-orbit robotics. And I'm trying to pull together academics from different universities all across the UK who can work together to develop our national space robotics programs in consultation with various industry stakeholders. We are hoping that through interacting with the Space Universities Network, we will be able to reach out to many more universities who will be very keen to, I believe, keen to support this national program. So this is another initiative we are driving through Lincoln. And of course, when it comes to space research, it's important to make sure, we are involved in ESA space programs, and we are contributing to various initiatives led by the European Space Agency. And in the recent years, we have been contributing to various technology harmonization programs jointly with the UK Space Agency and ESA. In particular, University of Lincoln has contributed to technology harmonization on model-based systems engineering, attitude and orbit control systems, hold, deploy, and release mechanisms. So there are quite different areas that we are contributing to the European space initiatives as well. Internationally, I'm pleased to report that there are a lot of opportunities for us, and I have been part of organizing various large-scale robotics programs. For example, the European Robotics Forum, IEEE's flagship robotic conferences like ICRA, IROS, and we are also working with various international experts from different agencies and, of course, academia as well, to develop programs or initiatives that will push the boundaries of space robots. And we are establishing our contacts with the UAE Space Agency as well, and we are looking forward to supporting some of their new programs, which of course, they are very successful in the recent years in sending their spacecraft to orbit and now to Mars, which is great. So we are working with various international agencies to grow the space research activities, and of course, my interest is to drive space robotics missions nationally and internationally. Let's slightly move from orbital robotics to planetary robotics. Of course, planetary robotics is much more popular than orbital robotics because we have heard a lot about NASA's successful missions to Mars, starting with the Sojourner Journal and now with the recent success of the Perseverance rover to Mars. Again, when it comes to planetary robotics, I try to focus on system design, mostly unconventional robots, micro robots, which are inspired by nature. So I wouldn't be, daring to build large rovers like what NASA has flown, but instead my interest is to look at innovative designs that will one day hopefully will fly. So I try to work on the rover design, the chassis design, the locomotion, how the different type of locomotion or the locomotive solutions interact with different type of planetary soils. We are also interested, or we are also working on developing sensor technologies that is needed on board these rovers for understanding or doing some in situ testing of this planetary soil samples. I work also on the concept of multi-agent operation, which extends to swarm robotics. So here, interestingly, my first encounter with a planetary or a lunar rover program was back in 2008 when the University of Surrey was selected by the European Space Agency to compete as part of their lunar challenge. Hats off to our students who put together a micro rover in a matter of 3 months. So this, as you can see, this is an unconventional design. This is a tracked design, which hasn't yet flown to Moon or Mars. Because if you look at the successful missions from NASA, very clearly these are wheeled vehicles. So because of the heritage, the success they have had in launching and operating wheeled vehicles, they still follow the same philosophy of launching or sending wheeled vehicles to Moon or Mars. But there is a potential for other designs as well. For example, if you look at the way insects or other organisms navigate, there are a lot of things we can learn from nature. So one of my interests is to really look at how, for example, walking robots can be built, which could one day become a scout rover, or they could work in team to explore Mars. The benefit of these smaller walking rovers is that they can really walk across craters and crevasses, unlike large wheeled vehicles. So there are clear pros and cons with larger vehicles and smaller vehicles. And of course, when it comes to wheeled vehicles, one other area we are interested is looking at monowheel and diwheel rovers. Again, this is not to completely replace a conventional large wheeled vehicle, but this is to really complement the operations of such large rovers. And with, if we are able to advance the technology of these systems, I'm pretty sure one day we will be able to fly multiple rovers, which will return back more science data. So again, we were a part of a study funded by the European Commission, and jointly with several partners from Europe, we were able to do the feasibility study of a Scout rover mission, which is very interesting because here, as you can see in the video, this is a hybrid wheel leg system. So what we offered to this project was, from Surrey, from my end, we developed a soil sensor which was embedded within this hybrid wheels of this rover. So this way, the rover can actually look at hidden dangers such as dew crest well in advance of the primary rover navigating through the terrain. So I'm just going to run a very short video to give you a better idea about the EU FASTER project, and then we will move on to other topics.
A novel concept taken through the stages of prototype, design, fabrication, and analysis focuses on two rovers working in tandem and the communication between them. Project FASTER advances the mission in a number of ways. To protect the primary rover from potentially hazardous terrain conditions, it is conceived that a smaller, more robust Scout rover can scope out conditions ahead of the primary rover. The Scout rover is capable of traversing both rocky terrain and soft surfaces through a hybrid wheel system.
Right, if you're interested to learn more about this hybrid locomotion and the way two robots could work collaboratively, you'll find some very interesting videos in YouTube, which is much more lengthier, and it gives you more details. Let's move on. So moving from planetary robotics to asteroid mining, how interesting is that? Well, we know that mining is a large business on Earth, and there are many companies who are heavily investing in mining. But now we see that more and more investors are coming forward to invest in robotic mining of asteroids. And one of the areas I'm working is connected with asteroid mining. This is a program jointly funded by Airbus and EPSRC, where we are looking at developing a self-reconfigurable undulating grasper. We call it SNUG. The philosophy of SNUG is very similar to what we see in nature. For example, we know how a python would capture its prey. That's through encircling its prey. But we don't want to behave violently like a python. We don't want to crush our sample, which are very valuable. So what we are trying to develop is a robot which is modular in nature, which can virtually encircle its target and gently, capture the sample. So when it comes to operating a robot in an asteroid environment, we know that the gravity is very low. So it's very hard to operate or collect samples using a traditional robotic arm. In fact, this is like, say, for example, trying to capture a housefly with your chopstick. It's incredibly hard to use the traditional manipulators. So we believe that the technology using the virtual caging principles will be more appropriate for low operating conditions. And now we are in a stage where we are prototyping the different parts of this robot. So hopefully in another year or two, we will have a working platform. Now, let me also say a few words about outreach and some of the activities I'm having with the student community. So when I say I'm a space engineer, it's very important that I should pass on my knowledge to the next generation of engineers or space engineers. And for this reason, since 2005, I have been very active in outreach and public engagement programs. And to date, I have addressed more than 10,000 students all across the UK. And this is, of course, this was initially facilitated by the National Space Centre in Leicester, and thereafter by, the Royal Academy of Engineering, and many other societies, many other professional bodies, and of course, universities and schools who help or support such initiatives. Even in the University of Lincoln, recently we formed our Student Space Society, and we are hopeful that once we return back to campus post-COVID, we will be, again supporting our students to take part in various competitions. So I'm looking forward to those brighter days again. If we have students attending this presentation, I would encourage you to register for the upcoming Student Space Society, the National Student Space Conference. So this is going to take place next month, and it's a fantastic opportunity for students to interact with experts from the space community and also meet other students who have similar interests. So this is another upcoming opportunity for students. Well, next, let's move away from space. Let's come down to Earth. Let me say a few words about my new initiatives in agri-robotics. Very limited, but very exciting. When I came to Lincoln for the very first time and had a tour of our facilities across 3 different campuses, I found it incredibly exciting place to work, because if you look at the volume of high-profile agri-robotics programs taking place in the Lincoln Institute for Agri-Food Technology, Lincoln Agri-Robotics, Lincoln Center for Autonomous Systems, and the EPSRC CDT, it's mind-blowing. Honestly, it's mind-blowing. It's very tempting to work full-time in agri-robotics. But of course, I'm trying to, develop my interest in space. But at the same time, I have some opportunities to apply my knowledge in planetary robotics and orbital robotics to agri-robotics. Here, for now, I'm only concentrating on electrical vehicles or electrification of farm vehicles, and of course, looking at how mobile manipulation can be applied for harvesting. And one other area I'm very interested is to really understand, how we can use robotic technology, whether it's ground-based or aerial robots, for mapping of soil carbon, because this is another big area, internationally, that is gaining popularity. And I believe, robots will play a big role in future monitoring of carbon footprints. If you look at the pros and cons, or the synergy between planetary soil and agri soil, there are quite a lot of differences, and of course some similarities as well. I started off with a background in planetary soil simulants, or planetary regolith, where we dealt with very fine particles, sometimes very powdery, very dangerous in terms of health hazards. Whereas now, when I look at applying those know-how into agricultural industry, of course, this is a big shift from micro management or micro engineering to macro engineering. Moving from micro rovers for planetary missions to large agricultural vehicles. Moving from electric actuators to hydraulic actuators. Well, my interest, as I said, it is to really look at the potential of growing electric vehicles for farming application. And therefore, again, the shift is that, of course, the size-wise, we are growing from I'm growing from designing micro rovers to designing larger agricultural vehicles. And the challenge there is not the size of the vehicle, but the size of the technology we use for actuating or driving these vehicles. But before I could even do any project in agri-robotics, I felt, I must learn more, because this was a completely new sector for me. Thanks to our colleague Sean, who gave us a wonderful training about the different types of soils we see in different parts of the UK, and various information about the weeds. So it was really nice to learn something very new, very different from what I used to do previously. We had a lot of fun playing around in the field. Oh, sorry, I meant doing the proper training in the field. And now I'm in a position to support my colleagues through an Inaugural project where we are looking at developing electric drive system for agri-robots. So these are intelligent vehicles, and the main difference is that rather than using hydraulic actuation, we are looking at developing electric actuation. And of course, with our project partners who comes from the sports industry, we are finding it quite amazing to see how some of the technologies they have developed can be now applied to the agri-industry. And we are hoping that in the second half of 2021, we will be able to demonstrate the operation of our vehicle for weeding application. So as you see in these images, traditionally, weeds are removed using either rotary hooves or tines. And these are, of course, mounted on large tractors. So we are looking at, rather than changing the art of weeding, we are trying to enhance the technology so that we get better efficacy. So this is another very interesting project that I'm now part of, and we are hoping that later this year we will have some nice results. Looking at the application of robotic manipulators for farming. Here again, I have worked on rigid manipulators for space applications. Of course, for space industry, we haven't yet proven the potential or the feasibility of soft robots. But we know that the soft robotics community is growing at a fast pace internationally. And when I came to Lincoln, I was quite amazed to see what is already going on in Lincoln in terms of soft robotic research for agricultural application. And I thought, okay, why not support this initiative, looking at how some of the knowledge I gained in designing medical robots. So there is a nice synergy in the soft robotic technology that connects medicine or medical application or surgical procedures with precision farming or precision harvesting. Now in Lincoln, we are trying to build a small group specializing in soft robotics. Oh, sorry, I forgot to tell you about my background in medical robotics. So let me just briefly tell you, how I encountered a medical robot. Well, when it comes to medical robotics, my husband is my guru. He is a surgeon and a GP, so I learned a lot of basic things about surgery and human anatomy from him. And with that information, I was able to interact with the clinical community and also other experts in the soft robotic community at various institutes internationally to understand what are the driving principles of a soft robot, what makes it different to the rigid robotic manipulators. Of course, I'm sure you have heard about the Da Vinci robot, which is very popular, and there are many hospitals all across the world who have invested in Da Vinci robot. As you can see, this is a bulky robot, it's a rigid robot. Of course, they have very high precision console through which the doctor or the surgeon can operate. However, it doesn't offer the feature of haptics, or in other words, the surgeon doesn't have a feel of what he's doing. So everything is visually aided. Unfortunately, this is a very expensive system, and especially in the UK, with NHS, it will be very hard to invest or to procure these systems. So if that's the case, how can this become a standard platform in other countries? So there is a need to look at other alternatives to the Da Vinci. Of course, there are companies who are now looking at rigid robotic technology, which are much more modular, unlike Da Vinci, which is a single large bulky system. If you look at the CMS Surgical's modular robot, of course it is modular, which is great, but this is again a rigid system. So in terms of its design, this is very similar to an industrial robot. Although, it might be having better sensing, which of course, we do have in other industrial platforms as well. So this is why I understand that the soft robotics community, which I'm part of, they are heavily pushing the frontiers of soft robots for surgical and other applications, including agricultural operations. So here again, as I said, there are very interesting lessons we can learn from nature, which helps us in designing soft robots. And we had the opportunity to work with various international partners on an EU-funded program that looked at developing a pneumatically actuated robot inspired by octopus to do different type of abdominal procedures. So my team, we were able to demonstrate this jointly with other partners for ex vivo testing, and the StiffLab consortium, they managed to do the human cadaver testing in partnership with the University of Dundee and our clinical partners on board. So clearly, there is a potential for soft robots because they can reach out to those parts within our human body that are otherwise inaccessible to a rigid robot or even a surgeon through open or the laparoscopic procedures. So there is a future for soft robots in the medical sector. And to me, it was also important to explore other clinical applications of soft robot. And therefore, I started working with the Royal Surrey County Hospital with the gynecological department. And we came up with the concept of a flexible uterine elevator, which can be used for a range of procedures such as hysterectomy and various procedures where they need to remove tumors from the uterus. So we are working with the clinical community in developing this concept further. We were able to do some preliminary testing or the feasibility, but the biggest shortcoming of a soft robot is its limited payload capacity. So unlike rigid robots, whether it's surgical applications, agricultural applications, or other applications, we want to develop or improve the technology level, readiness level of soft robots so that they can carry heavier loads. So this is one of the bottlenecks when it comes to soft robots. And of course, we are working towards, developing other innovative mechanisms, hopefully, which will change the art. So in terms of future development, there's a lot more we can do. And of course, all this will need funding. One other very interesting opportunity we now have jointly with some of the partners based in Cambridge is to develop this concept further and apply it to IVF. So when it comes to IVF, again, there are a lot of challenges, and we are exploring the potential of robotics and automation solutions to improve the quality of IVF. Of course, I'm not going into the details, but there is clearly a market for this. And we are working with our partners to develop this concept further so that we can commercialize it. So for that reason, I'm not, disclosing more, but it's very clear that if it is IVF, we cannot accept any errors. So this is totally unacceptable. And therefore, it's important that we provide a very precise solution to the patients. So we have our team on board, and we are working towards securing some funds to develop this concept further. Now I'm into my next adventure, which is interesting because this is really looking at how the concepts that we developed for medical robots, that's a flexible or the soft robotic manipulator, that technology can be applied to remote inspection and maintenance, or unmanned inspection and maintenance of industrial gas turbines. So again, when I came to Lincoln, I was very pleased to see the large-scale facility, Siemens facility in our campus. So again, I couldn't resist myself from entering the lab and learning more about how complex these industrial machineries are. So, we are really excited about developing this concept for internal inspection of gas turbines. And I'm looking forward to starting my post-COVID industrial secondment with Siemens. Similar initiatives are already progressing at other companies like General Electric, and also University of Nottingham is developing similar technology for inspection of aero engines jointly with Rolls-Royce. Now, I must say a few words about the nuclear robotics research at the University of Lincoln. My colleagues Mark and Amir, they are overseeing the activities of the EPSRC and CNR Hub at Lincoln. Again, this is a large-scale national initiative which involves various other partners, and the University of Birmingham is leading this initiative. So as part of this NCNR program, they are doing quite a lot for the nuclear industry. And interestingly, my interest here is to support our team in Lincoln, and of course our industrial collaborators, Veolia and faculty, through a new Innovate UK funded program that looks at developing a robot with a haptic teleoperation capability for sorting and segregating nuclear waste. So this is very nicely tied up with the ongoing programs or the activities within the NCNR Hub, and we are looking forward to kicking off this new project in near future. So overall, I would like to say that being a space engineer, I have a lot of opportunities to work not only with space-based companies, but also with several other industries. And there is a huge potential for cross-sector technology transfer applications. So in conclusion, I would like to say that a career in space engineering actually opened up several opportunities for me. And my control engineering background allows me to work on a range of automation and robotic solutions for different businesses. And I will continue, of course, to support innovation in robotics and facilitate cross-sector technology transfer applications. So hopefully this will help grow the capabilities, our regional capabilities in the East Midlands, and of course create new opportunities in Lincolnshire. So being part of a UK-led space robotic mission is indeed my dream, and I'm glad we are able to work with industry stakeholders and the UK Space Agency to develop our national space robotics programs. We will contribute to national and international programs as well. So I take this opportunity to thank the University of Lincoln for giving me this exciting role, and I'm glad my colleagues are incredibly supportive. So thanks to various research councils and space agencies, Airbus and SSTL, for funding my research. I dedicate this presentation to all my students and research fellows who contributed to various national and international projects. So I salute you for all your contributions. If you're listening to me from different parts of the world, a big hi from Lincoln. So with that, I would like to conclude my talk and happy to take up questions from the audience.
Thank you, Minnie, for that fascinating insight into your research. So we do have limited time for questions, but if you would like to add one to the chat, we can certainly allow Minnie to answer those for those of you able to stay a little bit longer. So I guess I'll jump in while we're waiting. What do you think is the single most exciting thing about the future of robotics in space for you at the moment?
I'm dreaming about a UK space robotic mission. Honestly, that'll be the most exciting thing for me. Although we do have opportunities to support or contribute to other international programs, I would really love to see a UK-led space robotic mission.
Fantastic. And oh. So lots of congratulations coming in there. That's brilliant.
Yeah.
Someone, so Fernando's asking, what about sound in outer space? He's a sound scientist.
Sorry, what exactly is the question?
What about sound in outer space? I
don't know, Fernando. Did you hear the recent release from NASA about the wind blowing on Mars? It's fascinating, but of course, I don't know much about sound in outer space. Honestly, I can't answer this question. Sorry.
And there's a quick question about how people are able to contact you going forwards. The best way is to go through the university website and search for you, and that will give a direct link. These slides will be shared as a video from the Lincoln Institute for Advanced Studies website. If you have troubles accessing that, then just drop us a line and we'll guide you in to find that.
I think there are some more questions coming up.
So what would you say, from David, what you'd say is the biggest challenge to overcome before we'll get that space robotic mission in the UK?
Well, the biggest challenge we face in the UK is lack of funding. So it's not the technology. Of course, technology needs more maturity, but space programs or space missions are very expensive. So there is a need for more funding to support space missions. Because one thing that most people don't realize is that space really revolutionized our lives. We use mobile phones, we use internet, everything is from space. So unless we can convince our government and of course the public to spend more money on space missions, we cannot innovate and we cannot benefit from the innovations we do on Earth. So funding is the biggest hurdle for us.
Great. Libby is asking, how can we encourage more women into this amazing field?
Well, yeah, I believe through various initiatives, local, national, and international, we can really pass on the message that there is a future for women in the space industry. Whether you like to work in the industry setting or in academia, like me, there is a bright future. So I would really encourage more women to come forward to become either a space engineer specializing in any area you like. It need not be robotics. It could be looking at satellites or communication, embedded computing, etc., etc. There are many areas. Space is multidisciplinary.
Great. So I think we've got time for a couple of questions more. So we have Nabeen asking, rare metal detection and extraction from planets has great potential in the future. What's your take on that? And I guess what the question is, what role has robotics there?
Robotics has a big role, and this is why we are looking at the potential of mining an asteroid. So we are discussing with the Australian Space Agency because in Australia, terrestrial mining is a big business, and Australian Space Agency is also interested in teaming up with the UK Space Agency and UK-based space businesses to explore the potential of mining other planetary bodies. and there is a huge potential. If robots can prove that we can collect samples, and of course we need to return it back to Earth. Only then, we can make money out of it, right? So without robotics and without automated solutions, it is hard. But this is why we strongly believe that to achieve any such missions, complex missions, we need robots in action.
Great. Thank you, Minnie. So the last question I think we can do is Stephen asks, isn't theft a huge challenge to robotics on farms? So how autonomous can these systems really be if they're an attractive target for crime?
Oh, that's right. Very true. Because the robots are more expensive than human laborers. I'm sorry to say that, but that's the reality. So there will be, especially when we have more robots in the field, there will be many other security-related issues coming up. But I believe with advances in 5G and other communication solutions we have, there will be means to keep them secured, independent of how big the field is, how open the field is, independent of the crime rates in that area. So I hope the advances in communication, and of course satellite communication, there again there is space contributing to that. There will be security solutions in place to keep all assets, farming assets, safe. But we need to educate the community about the benefits of robotized farming. I think that is indeed a challenge. Yeah.
Great. So thank you, Minnie. And before I ask everyone to continue,
I think there's one question.
I'm afraid we've run out of time on there.
Sorry.
I just want to remind everyone that on the 18th of March we have our next inaugural lecture from Professor Louise Wilkinson from the School of History and Heritage. So thank you so much, Minnie, and hopefully everyone can join me through the chat by saying thank you too for such a great talk.
Thank you, everyone, both my colleagues, students, and all external attendees. Thank you so much for joining us today. Thank you. Bye.